Transition to our next speaker. I'll go ahead and introduce him. So our next speaker is Dr. Giuseppe Pileio from the University of Southampton. He'll be talking to us about long-lived nuclear spin order, theory and applications.
All right. Good. Can everyone hear me and see the screen properly?
Yep.
Okay, thank you very much. Okay, great. So very nice conference so far. Really enjoyed it. And I have to say, I feel a little bit out of place because, as you know, parahydrogen is not really my expertise. However, I was asked by Thomas to give like an overview of long-lived nuclear spin order. In particular, discuss the content of a book which I edited recently for the Royal Society of Chemistry. And I couldn't resist actually of trying to do some parahydrogen experiments of my own, which I have to anticipate I didn't succeed because of the lockdown, but I'm gonna, towards the end of the talk, I'm gonna discuss an application which has potential when it's coupled to other polarization technique like Parasaber. So, great. Okay, so the book I'm gonna discuss in this first part of the talk is this one here. So it has been written by a number of authors. You will see in the acknowledgement slide, who they are and so on. But essentially the idea here is to collect for the first time what has been the result of the last 15 years of research in the field of long-lived nuclear spin order. And the content is basically divided into 4 sections. So we start talking about the property of the spin order, and then the experimental techniques which we and other groups have been putting, basically publishing in order to manipulate the order. And then there are application of singlet order and other forms of long-lived spin order discussed towards the end of the talk. So the idea here is to actually walk you through the book, kind of using the same kind of philosophy, some my kind of ideas, or let's say the way I see the argument and what is the most important bits of it. So let me just introduce the topic. Obviously, I don't have to say what is a singlet order in this audience. I still want to make a point there. So singlet order is the order which relates to a pair of spin-half nuclei, for which we have 4 energy levels, which you see there in the slide. And you can basically make transition between those levels through radio frequency pulses, but the levels are actually connected to each other through relaxation mechanisms, which ideally, well, you basically can see them as an exchange of energy with the molecular environment, the lattice. And this is mediated by a number of relaxation mechanisms. And here you see it in this arrow here. I have divided them into 2 main parts. So the dipolar mechanism, which in fact I mean the intra-pair dipolar coupling between the 2 spins in the singlet pair, and all other mechanisms. So bear with me for a second on that. Now, Malcolm Levitt, about 15 years ago now, I think I understand from talking to him, inspired from the work on parahydrogen, thought about, well, if we change the magnetic or electronic environment, those 4 energy levels will appear more like 2 manifolds, a singlet and a triplet one. And the triplet is still connected to the molecular environment through the same relaxation mechanisms as before. Singlet and triplet are also connected to each other through a difference in chemical shift between the 2 spins, things that you don't have in parahydrogen, obviously, but in a general molecule with 2 spins, you may have a difference in chemical shift. Now, the point is that nothing has changed so far, but if we manage to actually suppress this chemical shift difference, we can isolate the singlet state, and we have there this isolated state, which actually relax to the lattice, immune to the dipolar mechanism, which is often the most important one, at least when we talk about liquid state NMR in non-viscous solvents, small molecules. However, the other mechanism labeled there carries also a star, and this means that under studied circumstances, this link to the lattice is also weaker with respect to the link with the triplet R's, that the triplet R's to the lattice. So in that sense, the singlet R's is long-lived with respect to longitudinal magnetization, which belongs to the triplet main folder. Now, it has been essentially my job for about 10 years as a postdoc in Malcolm's group and later in my own group to tackle all these relaxation mechanisms and try to understand them theoretically. So what I've been doing is basically I've gone through a series of mechanisms and trying to derive analytical equations wherever possible, some using approximation and so on. And then we use that information to figure it out how we can minimize those mechanisms. Now, this has been discussed by myself in chapter 3 of the book. And there is like a nice table, I think, which reports about the relaxation rate of the singlet order as for each of those mechanisms connected to the molecular or the spin system parameters. So what you can do with this information here is that what we have done is basically talk to our co-workers in chemistry in Southampton and try to change those more theoretical aspects of the discussion into practical, how to say, features that a molecule should have in order to display longer and longer lived nuclear spin order, singlet order. And with those collaborators, as discussed by Linda Brown, which is one of them in chapter 4 of the book, we came out to a series of rules, and she discusses about a number of molecular cores that can be used to create this long-lived spin state, and surely to take inspiration to create even a larger categories of molecules we have, which possess these particular features. Now, the record molecule at the moment is this doubly labeled substituted naphthalene core, which in some circumstances has displayed a singlet lifetime of nearly 2 hours. Now, the second part of the book is about how we manipulate the order. And if you remember in the first slide there, I talked about we have to suppress this difference in chemical shift somehow. And this means switching the symmetry of the spin system in some sense, right? And, or if you want, you can see it as changing the magnetic or electronic environment. And we and many other groups actually in the world have took the challenge to actually provide or investigate the field and provide methodology in terms of pulse sequences and other form of manipulation in NMR, which accomplish this task. So essentially convert the silent singlet order into observable magnetization and vice versa. And this can be done by field cycling, chemical transformation, synchronized spin echoes, slick or spin logging induced crossing, and adiabatic passage or upsoak. This has been discussed in these 5 chapters in the book. And I'm not going to spend any more time. I mean, many of those techniques, in fact, have been described already. And I'm really happy to see that this community actually uses a lot, obviously, for obvious reason. So I'm going to move a bit into the application side. So the chapters about applications, I'm not going to go through all of them, of course. I just want to talk about a few applications which relates closely to this meeting. But before to do so, again, in the promise of trying to show you how I reason when I discuss these things with my group and so and colleagues, the singlet order is often recognized to be like long-lived, but this is not just, this is probably its main properties, but it's not the most important one, if you see what I mean, in the sense that there are 2 other, at least, features which are very important and which you always have to keep in mind. The order is actually silent, so it doesn't provide a signal, an NMR signal on its own, and it's also for the same reason somehow, or you can derive from that, that is accessible on demand. meaning that it is, in particular, is actually immune to radio frequency pulses or field gradients, actually, unless you have this clever methodology that we discussed, the previous slide, in which we actually finally tune pulse sequences to the spin system parameters. So when you put together these three features, you will agree with me that a singlet order is what I would call a long-lived smart tag, which can be exploited in magnetic resonance. And I wanted to be general using the term magnetic resonance because there have been applications already in both NMR and MRI field. Now, obviously, the first application, I'm sure it came to your mind, that most of you are actually using it already in the field of parahydrogen, is the storage of hyperpolarization. So you use the order, this long-lived order, to store polarization, which in this community is gained through FIP and Saber, and but it can also be, provided by the solution DNP and other technologies. Now, this is discussed, and I'm gonna stop a little bit on these 2 points in the book, but there are also all sorts of other applications which have been derived and described in the book. For example, measuring drug affinities or molecular interaction biomolecules, expand the scope of exchange spectroscopy, application in quantum computing, and so on. And there is also a number of other techniques which have to do with translational dynamics, which are mainly developed by my group, which includes like measuring of diffusion, slow flow, diffusion tensor imaging, Q space, and so on and so forth. Now, I'm going to go through really very quickly to applications which are discussed in the book related to this topic, to the topic of this meeting. So chapter 18, written by Kerstin Münnemann and co-worker, is about applications or combinations of FIP and singlet order. So for example, Kerstin there discusses how you can take a molecule which contains a triple bond, and then which is easy then to parahydrogenate. And then once you undergo the reaction, the molecule is actually chemically, the 2 protons are chemically equivalent, but magnetically inequivalent. And so you can store the polarization there for minutes. And then the fact that they are magnetically inequivalent allows you to convert it into some form of observable transverse magnetization, basically. And Kerstin discusses you can do that by field cycling, SLIC, as I was saying before. Definitely you can do it by M2S and other techniques, and also some more specific techniques developed ad hoc, like off resonance irradiation or chemical shift scaling. Now, we have been active, in fact, ourselves in that field, as has been actually shown yesterday by James in his excellent talk. In fact, we were discussing how we can convert the hyperpolarized singlet order after FIP hydrogenation of a triple bond into heteronuclear magnetization. And we came out that you can do that with a simple SLIC methodology, as the one published by Devins and Met. We also developed a new methodology, which is based on our M2S S2M sequences, which again, using this synchronized spin echoes, deposit magnetization, hyperpolarized in this case, from the singlet into heteronuclear, in this case, unlabeled C13 in the molecule you see there in the slide. This has been discussed in the book by Gabriele Stepanato in chapter 11. Sumia Roy, previously in Simon Daggett group, and now in Southampton, actually back in Southampton, has been taking the challenge to combine Saber and singlet order, and discussing that in chapter 19 of the book. He basically, essentially he showed that you can create those molecules which are hyperpolarized, as you see. They can, depending on how you do it, you can get, how you do the Saber. If you do it in low field, you can get straight, like singlet order hyperpolarized in the target molecule in the final molecule there in the substrate, let's call it. And or you can have longitudinal order, and in that case you will have to, or you may want to convert it into singlet order to improve the storage time. And he did that with an M2S as discussed in the chapter. Now, this is all about, I wanted to say really about the book, other than adding, if you are interested, as you can see in this meeting, is very important for this community as well. So if you want to read about, go on and buy it. Now I want to switch a little bit and discuss a technique which we are developing in these days, or just before lockdown, in fact, and progress has slowed down a lot, as I imagine in every other lab. And this has to do with singlet scan measurement of TS. And I would say a subtitle would be for cost-effective discovery of long-lived spin state. And probably another subtitle would be in combination with Saber or parahydrogen, or even more generally, hyperpolarization techniques. That's why I think it's important to report about that here. So let me make a picture, paint a picture first of all. The most common experiment we use to measure TS is not suitable for hyperpolarized substrates. Now this experiment is very similar to what we use more generally to measure T1, right? It is shown, one of the versions is shown here. So you have a singlet destroy technology to start with, which is not very important in the first scan, but it would be important if you are left with singlet between scans. And this has been developed by Konstantin Ivanov and co-workers in Novosibirsk. Then this ensures you that you have to wait actually for a few T1s rather than a few TS. And we know that TS is significantly longer than T1 most of the time. And then you create some singlet order. I've cited here M2S, but it could be like the SLEEK, it could be APSOC, any other methodology. And once you have that, you have a variable time delay. Then you may have a filter to filter out byproducts, and then S2M to convert back into magnetization and therefore acquire a spectrum. Now, you do this experiment and in pseudo 2D mode. So you have to acquire a number of points in the time variable and wait every time to basically replenish thermal polarization. But if you work with hyperpolarization, you will have to repeat the hyperpolarization steps, which, for example, in DMP means prepare another sample, which may take another hour, and so on and so forth. In FIP, you have to repeat the reaction and so on. Now, these are also time expensive experiments, which are essentially day long, because when you have like a TS of an hour to measure and a T1 of 30 seconds, and you want to take, say, 8 points or so, it will take about 10 hours per scan. Now, we have been through that, right, discussing about can we speed up this methodology and can make it suitable for a single shot technique or single scan technique, so to be compatible with hyperpolarization. And already in 2013, we have published a paper in which we provide two methodologies. The first one would be something similar to that one. Again, there could be like many variants. So essentially, you start with hyperpolarization gained by whatever. In that particular paper, we were collaborating with Jan-Erik and Pierre Larsen, so we were using the solution DMP. And then you use M2S to actually create hyperpolarized singlet order from hyperpolarized longitudinal magnetization. And now you can have like a fixed time delay and truncated SLEEK or truncated S2M or whatever. And this will bleed a little bit of the singlet pot at a time. You take an acquisition and then you repeat, bleeding another bit, and so on. Very similar to the small flip-angle pulse they use to measure T1 in hyperpolarized experiments. A better way, we think, would be to actually recycle the whole signal content. And to do that, we propose this methodology here, in which, again, we start with the solution DMP, and then an M2S to create the whole pot of hyperpolarized singlet states. And then we can store that for a given period of time T, And then we have S2M to S, which is expanded down here. We have S2M followed by M to S, but in the middle we have a double echo, a perfect echo, as known in the community, or a triplet echo as well, which is needed actually to be able to restore the singlet into magnetization and then back into singlet. But also during the echo time, we can collect at least 4 FIDs and then basically keep repeating that procedure. So instead of wearing up pseudo 2D and having to have a variable delay, now we have a long FID, which we can split into pieces and have a single basically scan, having gone through a number of time in the time variable array of a normal experiment. So today I'm going, well, actually, by the way, the experiment on the top, essentially each acquisition only reads a very small amount, the one we decide of the total polarization. So it may be a bit inconvenient because you throw, well, not thrown away, but let's say you use only a bit of the available signal. The bottom one, actually, the whole polarization is used at once. Although every time we go from the S to M, M to S, we lose because of imperfection and other reasons. So the decay is not pure at TS, but it has like a penalty which has to be calculated and factorized in order to extract the TS. Well, what we are working now is actually to use SPAN technology, so spatial encoding, to accomplish the same task. So the idea came from some less recent, I would say, developments in my group, in which we were developing M2S, space selective M2S and S2M pulse sequences, which again accomplish the transformation between magnetization at singlet and vice versa, but they do it in selective areas of the sample, selective slices of the sample, for example. So the way we use that, so we have been using that in different ways in conjunction with diffusion experiments and so on. But in this particular case, the way we are going to use it for a single shot measurement of TS would be the following. Space selective M2S is run, and for example, addressing a 1 millimeter thick slice at the bottom part of an NMR tube sitting in the coil. Then you get tau SL, so you wait for some time. And then instead of reading, you go back a number of times and change the offset of the shaped pulse, which features in the selective M2S. And this means that you address a different slice of the same sample, perhaps 2 millimeter above, again 1 millimeter thick, and put the molecules in that slice into singlet. Then you wait another time and keep repeating that. And essentially you can do that fitting a number of slices within your active coil region. Once you're finished with that, you have obviously the first slice you have addressed has been there for NR times the tau L, while the last one only for 1 time tau L. So you have reconstructed the whole time variable time array in one go, right? Then you can filter out byproducts with a T00 filter, and then a non-selective S2M, we convert singlet into magnetization wherever it is in the sample, so across the whole sample. And now you do a 1D spin echo imaging to reveal the status of the sample. So let me walk through what you should see. Well, if you isolate just a 1D spin echo imaging system, you just get the profile of the sample. In fact, if your sample extends above the coil, right, you see the profile of your coil. So not very interesting information. Now, if you prepend a M2S filter S2M block, you get exactly the same information, but you lose signal. Now, we know theoretically that you should lose 1/3 of the signal. Now, experimentally, we are losing about 2/3. We don't know yet why, but let's say we didn't have time to investigate that. We will do that, obviously, soon. Now, if you change the M to S with a space selective S2M, as I was proposing before, then you get a number of peaks. Say you address 7 slices, 1 millimeter thick, every 2 millimeters in the sample. You get, within the profile, you reveal these 7 slices. In this experiment, obviously, I put the tau SL to 0, so there is no extra decay. Now, the task would be actually to put a decay, to leave some time. Now, to cut it short, in this experiment, you fight with convection, thermal convection. In fact, when you measure like minutes long or tens of minutes long spin states, actually the molecule have time to random walk, so to do diffusion over millimeter time scales. So they actually can, can go from one slice to another one. So we have to stop that happening, and we find out that the best way would be to put a plug into the NMR tube, so a plastic rod where we precisely machine like slices of 1 millimeter, whatever we want, separated by the distance we want, fitted in the middle of the coil, for example. So now you see, if you repeat the experiment I was showing you before without leaving any time in between, the top experiment here, you have very nice sharp peaks, each one corresponding to the signal coming from one of those slices. Now, if you start leaving some time, 30 seconds or 70 seconds, the signal in each slice start decaying because of TS. This is a single shot experiment anyway. So once we have the image, we can integrate separately those 7 peaks and plot those and basically and fit against an exponential decay and get the value of TS. Now, in this particular case, the experiment is 4 times faster than, more than 4 times faster than the conventional approach. But actually it turns out that if you consider measuring like very long-lived spin states, the limit is actually the time array, not really the time you wait before, and the factor you gain is essentially a factor of 2. But I finish here, but the only thing I want to say that this experiment, we want to, now with the help of Sumia, which is also in Southampton, we want to combine it with Saber in order to be able to take molecule without the need to have a costly and time expensive synthesis of double labeling or whatever, and look at natural abundance pairs of carbons, for example, and therefore spot if we have, and how long is the spin state or the long-lived state in that case, for molecule which may have some sort of biological activity or biological compatibility or any function we want them to have. So that is a very precious tool, we believe, in combination with parahydrogen and other techniques of hyperpolarization for the quest of molecules which have long-lived spin state, right? But without going through, or at least at the beginning, without going through the synthesis and even the complex analytical and simulation required to actually predict how long that state will be. So I stop here. I just want to thank the people involved. So on the left-hand side of the slide, you will see all the main author of the chapters containing the book. So once again, thanks to all of you and the authors for their contribution, the Royal Society of Chemistry for inviting me to do so. And on the right-hand side, you see the people, so Julia, Kira, and Jean-Nicolas Dumais, which are involved in the work with SPAN methods for TS. And I thank you, obviously, and open to questions now.
Oh, great. Well done. Yes, we do have a few questions. First question, how can losses due to imperfections in the pulses be quantified, specifically referring to slide 15? How much losses are there if known? And then just a comment to add on that spin is a brilliant solution.
Yeah, so, well, as I said, I mean, we didn't have the time yet to do that. But the way it usually goes is that there are, typically there are, how to say, so the echo time has some length which has to be calibrated with the J, right? So the coupling. In this particular case, for example, those delays are 30 milliseconds. And you have to do that many times. So the whole pulse sequence, lasts like hundreds of milliseconds. So you have some sort of T2 relaxation. But that's just, yeah, okay, this is usually not very severe. But a problem we will have here, which don't have with classical M2S, is that in classical M2S, we have, because we have a lot of pi echoes, we have like some sort of phase cycling, actually sort of MLEV phase cycling within each echo train. We cannot do that easily when we have like the combination of selective pulses and gradients. I'm not saying it's impossible. We didn't go through that pain, let's say, yet to do. But I think those are the sources we have to look into.
Okay, a couple of potentially related questions.
Yeah.
Why is the spin experiment better than just using a small flip angle to excite a fraction of the spin order before M2S, as was demonstrated by Pepe back in 2013?
Well, that is not exactly what we demonstrated, because if you do like a small flip angle, right, you, how to say, you, well, essentially don't get the same results. The trick would be actually to, because you don't have the magnetization stored in the singlet in the first place. So you will have to, you may want to store the polarization into the singlet order first, right, as I show here. But then you want to bleed a little bit of that, right? So I'm not saying that the two experiments are equally valid, essentially. So I would say it's just a different methodology to accomplish the same thing, let's say. So we are going on, to do both, actually.
And have you considered using variants of M2S which have improved efficiency, for example, GM2S?
Yeah, okay. Well, we haven't, okay, I have to say we haven't implemented the AG M2S or the GM2S yet in my lab. Usually because we are not after, how to say, we are not after signal to noise, right? At least until you do applications. And we are a methodology development group, so we are not really interested, I mean, not particularly interested in that signal yet. But indeed, there are these methods, and we know, for example, I mean, APSOC, for example, developed again by Konstantin Ivanov and co-workers, it has already demonstrated they reach like the maximum theoretical conversion possible, right? So I mean, indeed, the methods are there. However, a method like APSOC or SLIC, they are not really fully compatible with my field of interest, let's say, which is like the use of this technology in diffusion or translational dynamics, where you would need actually strong pulses in order to couple with gradients and do space selectivity. So that's why you always see me actually using M2S rather than SLIC and other things, not because obviously M2S is something that we developed in Southampton, but really because for this particular set of experiments, I think it's more suited. But those techniques, especially APSOC, they're much greater. I'm gonna say it right loud, so no problem at all.
Okay, we have a comment from Malcolm, but I think we'll have to move on to the next speaker, so he's going to get the last word on you, I'm afraid. He says, I think I disagree with Pepe here about the equivalence of the repeated S2 M2S experiment and a small flip angle experiment. So I think that's a good discussion to take to the Slack window. And I will now go ahead and move on to our next speaker, but thank you very much for a great talk, very thought-provoking.